Hello? It's working, the microphone? Yes? Okay. Well, I'm glad to be here today, this cool day. And I think I'm speaking on behalf of a long record of Spanish astronomers who have been in collaboration with Dave Koo and people at Lick Observatory. We can go back to 1989 when Javier Gorgas was here, and perhaps the last one for the moment is Guillermo Barro, who is the new Candles postdoc here at Lick, and he just arrived 5 days ago or something like that, no, Guillermo? So I'm going to introduce you a long-term project that we started discussing with David back in 2004, and which is the main subject of one of my PhD students, who is Víctor Villar. This work has been done in collaboration with several people belonging to the Universidad Complutense de Madrid in Spain, Pablo Pérez González, Sergio Pascual, Guillermo, and the rest of the AG's collaboration. The project is focused on the star-forming galaxies and tries to provide a complementary approach to the large spectroscopic surveys. And the motivation for the project is that we already know that the local universe is where, well, we have there the ellipticals and spirals already in place. We already know that there is a decrease in the cosmic star formation rate, density, and we also have a clear idea that at redshift above 1.5, at redshift close to about 2 or 3 or even higher, we are facing the formation of the Hubble times. We are going to find a maximum of star formation rate density and the quasar activity. So in that sense, when we address the universe at about z equal 1, we are addressing a universe which I say is in transition, meaning that ellipticals and spirals have to be still forming, or at least we had that idea at that moment. And we should be able to see there the main reason why the star formation rate density of the universe starts to decrease. This is why we decided to work on one specific region in redshift, which is for this project at 0.8. And the idea was not only to produce a sample of objects, but to study them in as much detail as possible. What about the H-alpha approach? Well, the idea here was to obtain deep, narrow band images tuned to the H-alpha emission line at redshift 0.8. And why is that? Well, because H-alpha is an excellent current star formation rate tracer. It's even sensible to the AGN. If we use the same technique selecting the objects because of their H-alpha emission in the narrow band filter at different redshifts, we will be using the same res frame selection criteria. The narrow band also provides us the total line fluxes, and we don't need aperture corrections. And because we are working with a line selected sample, we can say that we have a well-defined volume. The sample is going to be complete and representative. And moreover, usually, because we are only selecting in H-alpha emission, we turn out to have a wide coverage in the parameters space. Of course, we decide to go to well-known fields. For example, I'm going to present here results for the extended growth strip and the Goods North field, and that was mainly because we had there the thousands of spectra coming from deep and deep 2, and the broadband data and all these complementary data. So the main data using the narrow band filter was obtained using the 3.5 meters telescope at Calaralto Observatory there in Spain. We performed 2 different surveys. The first one was in the growth strip. The second one was in the Goods North field. The kind of fluxes, or the fluxes we reached, were down to sometimes 10 to the 17th. And the total area explored was not very large, but about 600 square arc minutes. For this specific redshift, at the very end, we had a sample of 165 H-alpha emitters. And for them, we were very happy because we had, coming from deep, 94 redshifts for them. The multi-wavelength data came through our Rainbow database. I think most of you already know the huge effort that Pablo Pérez González and Guillermo Barro and the rest of our team, we have invested in this database to have a user-friendly interface, to have all the data in a common framework, to have all the data with the same apertures, with the same procedures. And in this way, we have not only optical, but also infrared imaging, Spitzer data, Galax, HST data coming from the ACS, and of course the optical spectroscopy. The first results we produced were published by Villar collaborators in 2008, and of course it was the H-alpha luminosity function. Please be aware that when we compute this luminosity function, we are applying one individual extinction correction per galaxy. We are not applying here a systematic correction or an average correction, but we are applying here one extinction correction per each galaxy, which is turned out to be very important. And we also produce the typical dot in the Maddow diagram. This is the star formation rate density at that redshift. But what was more important for the project was that we had not only the value at Z.8, but we also had the results from similar surveys at redshift 0.24 and redshift 0.4. And of course, we had as a reference the now classic paper by Gallego and collaborators back in 1995, which corresponds to these 2 points, depending on the way you compute the H-alpha star formation rate. What about the morphology? As Sandy already mentioned this morning, it turns out that these galaxies, they are already there. The redshift 0.8 turns out to be a little bit late. We can see already very well that we have most of the objects are disks or spirals. There is a small fraction of mergers, and of course we have a fraction of our regulars and compacts. We can even go to analyze the ACS data and, for example, to obtain fractions of flocculent objects, grand design galaxies, and so on. What about the extinction? For example, we can play here a game, which is because we have the luminosities at many wavelengths. We can play here the game, assuming that all the star formation rates have to be equal. For example, if we decide that star formation rate at the UV, H-alpha, and infrared are equal, then we can obtain, what you see here is extinction constant versus wavelength. One single dot is for each of the galaxies. You see here different extinction lobes, Cardelli 89, Cardelli 2000, Cardelli 89, and we obtain average values at those specific places. So if we want to have same extinction for the stars than for the gas, then we can obtain a specific value for this Calcetis constant, which turns out to be, for our sample, 0.53. Okay, so we could even assume that, or we could think that the gas for these objects would be less attenuated than in local starburst. We also obtain that we don't see any extinction bump for these objects. What else about the extinction? Okay, when the object was selected or was detected by MIPS in 24 microns, we used the ratio between the flux in the infrared and in the ultraviolet to obtain a dust oscuration, following the Buat and the collaborators 2005 approach. If the galaxy was not selected or was not detected by MIPS, we just use the UV slope. Using this approach, we obtained the extinction for H alpha, the absorption, and then we obtained that on average, the star-forming galaxies at z equal 0.8 have extinctions which are half of a magnitude higher than those at the local universe, which is pretty interesting. And this is very important because you can see many papers applying an average extinction for H alpha, which is assumed to be 1 magnitude. And this is completely okay for the local samples, but this is not okay at all for higher redshift samples. For example, you can see here that as soon as you reach 0.8, your average correction should be at least 1.5 magnitudes. What about the star formation? We can compare tracers. For example, what you see here is H alpha, the star formation rate based, H alpha based star formation rate versus a UV based star formation rate. In this plot, you have both tracers extinction corrected, and they more or less agree properly. When you compare infrared versus H alpha, you also obtain a good correlation. But of course, all of us, we always find out an scatter. Could we say anything about this scatter? What you can see here is a correlation between the ratio between the infrared-based and the H alpha-based star formation rates against H alpha equivalent width. The H alpha equivalent width is giving us a feeling, at least, about the weight of the young over the evolved population for each of the galaxies. So we could say here that at least part of the scattering could be explained due to the difference in age for the galaxies. This is something that is already observed in the local samples of H alpha emitting galaxies. What about the stellar mass? Okay, well, you have here the plot between stellar mass and H alpha based star formation rate, extinction corrected. Of course, the star formation and the stellar mass are correlated. And the slope we found for this H alpha selected sample of star forming galaxies at z equal 0.8 is in a good agreement with previous samples, for example, the Noisky sample, 2007. The mass and the specific star formation rate are anti-correlated in the sense that galaxies at this redshift have higher specific star formation rates than the local ones at the local universe. Of course, this is an observational evidence of downsizing. We should try to say something else about this. Well, our idea was to approach or to follow a similar approach to the one that published by Bandy collaborators from the DEEP collaboration back in 2006, where they plot, they produce a plot similar to this one, where you see something called quenching mass, or the quenching mass versus redshift. Their results were based on morphology, on color, and kind of star formation rate inferred from O2 emission. Our idea was to reproduce the plot for our H alpha sample, estimating the star formation rate now from the H alpha emission. Of course, you have to play a little bit of game to produce the quenching mass. In this case, we used a doubling time related with the specific star formation rate, and we applied the technique, also performing some simulations and quite a little bit complicated path to obtain quenching masses for the local reference sample, the one I published in 1995, and our sample at z 0.8. The idea here is that we were able to produce these two new dots. The red one over here is the one at z equal 0.8, and the red one over here is the corresponding to the local sample. And in this way, we obtained an evolution which turned out to be compatible with that found by Bandy et al. by Bandy and collaborators in 2006. But remember that this result is coming from a completely or complementary sample. It's not only a complementary sample, it's a different sample selection, and it's also a different technique to compute the star formation rates. So conclusions, the results have been already published. Most of them are in Villar Collaborators 2008, and the last ones have been published a few weeks ago at Astor PH. This is the reference. And just to mention that, well, you have here a list of conclusions, but perhaps the main one is that we estimate an upper limit to the quenching mass, close to 10 to the 12 stellar masses, which turns out to be an order of magnitude higher than in the local universe. Which is going to be the future? Okay, for us, the future, of course, is to obtain follow-up spectroscopy in the near infrared, and we hope that will be done following the collaboration that will be done using not only MOSFIRE at Keck, but also the Spanish MOSFIRE, which we call it EMIR, for the Spanish Keck that we call GTC. Thank you very much.
Okay. Any comments? And there was a request that the people who speak in discussion speak up. We don't have microphones.
I think the question of how we define a quenching mass is really interesting, so I'd like to give you another 3 sentences worth to expand on that point.
Well, in our case, we define what we call a doubling time, which tell us how long will take for that galaxy to duplicate its stellar mass, if its current star formation stays constant. So in that sense, a galaxy with a large doubling time would evolve or will evolve slowly, whereas galaxies with a small one would evolve quickly. So we define a quiescent galaxy when the galaxy has a doubling time which is larger than what we call quenching time, and the quenching time is assumed to be 3 times the Hubble time. Then you have to obtain or to translate that to a quenching mass, and in order to do that, we perform some simulations. In fact, there were several thousand simulations per galaxy, assuming the range in the sorry? And then when we mention here a quenching mass is something that we should call it upper limit for the quenching mass. In fact, this quenching mass, the quenching mass we obtain, it doesn't correspond with any of the stellar masses of the sample. It's a value which is larger, something that we kind of extrapolate. So, yeah, I agree that it's something still difficult. Go ahead.
Can I just ask one more question? Why is it a good idea to assume that the quenching time should scale with the Hubble time?
Quenching time.
You said TQ equals 3 times TA.
Well, it's just to be sure that you have produced all the mass related with the stars.
It's something to think about.
Yeah, definitely.
I just wanted to follow up on your point about the extinction. Can you test the Calzetti extinction law? For example, do you know whether or not the grayness of the extinction changes with redshift? And the reason why I ask is because this might reflect something about the clumpiness of the ISM and the relative importance of absorption versus scattering.
Well, theoretically, we could test it. The problem is that we are playing here a little trick because we are more, when obtaining the star formation rates, we are more or less assuming the Calzetti's law, So, but yes, in principle, you could test it. If you obtain similar samples at different redshifts and you have the different star formation rates, you could test it, of course. But you can see here, you have, for each of the galaxies, you have 1 point, and then you have average values. so you can produce an average extinction law for your sample, which would be in this case, well, as do you? I mean, I don't know if you understand, but you are playing here a small trick, I think.
Okay. Anybody else? Okay, let's move on.